Good day and welcome to our webcast titled What You Need to Know About Hydrogen Purity and Dewpoint for Large Turbogenerators. I'm Matt Grant, Associate Publisher of Power Magazine. For today's program, we'll hear from Steve Kilmartin. Steve is Director of Products and Markets for E1's Utility Systems business. Considered as a leading expert in the field of generator monitoring and maintenance, he has authored numerous papers, including work as Principal Investigator for the Every Turbine Generator Auxiliary Systems, Volume 3, Generator Hydrogen System Maintenance Guide. Mr. Kilmartin began his career with E1 in 1988 as an instrumentation specialist. Prior to that, he worked in the instrument shop at GE and also as an applications engineer at Mechanical Technology Incorporated in New York. His career has taken them in and around large machines and around the world now for over 30 years. Now, for those in our audience, at this point you should see a survey question on your screen. If you could be so kind as to answer this for us, it would be very much appreciated. This presentation will last about 35 to 45 minutes, and we'll follow up with a question and answer period. Before we get started, I would like to point out a few housekeeping items. At the left of your screen, there is an area where you can type and submit questions to the speaker. Feel free to send in questions at any time during the presentation. At the end of the program, we will answer as many of these questions as possible. For any questions that are not answered, we will try to answer them by email after the program. If you're experiencing any technical difficulty, you can type that problem in the same area at the left of your screen, and our production staff will assist you immediately. This program will be archived on our server. For future viewing, it will remain free of charge. You can use the same URL to reach the archive program as you did to reach the live program, which is www.powermag.com/turbowebinar. A certificate of completion for professional development hours will be sent out via email to every registered participant who attends. And before we begin, we would like to thank E1 very much for underwriting today's program. Their generosity actually allows everyone to attend the presentation at no cost. So with that, I will turn the program over to our speaker. Steve, take it away.
Thank you, Matt. As Matt mentioned, I'll be presenting on hydrogen purity and moisture monitoring and hydrogen-cooled generators. And because of recent events at several utilities in the United States, I'm going to be spending a little time on measuring gas purity during the purging of these hydrogen-cooled generators. This presentation is all about safety, increased efficiency, and risk mitigation. We're going to talk about why hydrogen is used as a cooling medium in generators. We're going to talk about the importance and why you want to monitor hydrogen purity. And as I mentioned, we're going to spend some time on discussing gassing and the gassing and degassing process. Sometimes this is referred to as purging the generator. And then we're going to talk about the importance of dewpoint monitoring. In the late 1930s, there was an increased demand to get more megawatts out of the generators. With generators, more megawatts means more iron. They got to get bigger. And also more heat. More heat is generated as you increase your megawatts. In order to satisfy the demand for power without increasing the physical size of the generators, a different method was needed to cool the generators. I find it very interesting that someone decided it would be a good idea to cool a generator with a flammable gas like hydrogen. However, the idea worked, and now all large generators are cooled, at least to some extent, with hydrogen. Why hydrogen? One of the reasons is that hydrogen has less windage losses, less frictional losses. Hydrogen is 4 times less dense than air. What this means is that you can create more megawatts with less horsepower. It is not as difficult to turn the generator with hydrogen versus air. Also, hydrogen has better heat transfer characteristics. it is 14 times more efficient at removing heat than air is. And as I mentioned, when you increase megawatts, you not only increase the size of the generator, but you also create more heat. Again, more megawatts means more pounds of iron. The generator gets larger. This chart gives you an idea of the differences in the specific heat capacity of hydrogen versus air. You can see when hydrogen is at 45 psig, it's about 14 times, has 14 times the specific heat capacity as air does. And also note that the density on the far right, that when hydrogen is pressurized at about 45 psig, it is 4 times less dense than what air is. There are additional benefits for using hydrogen. Because the generator has to be sealed, because the hydrogen has to be kept inside the generator, you have a sealed environment. So this prevents contaminants from entering into the generator. Contaminants such as coal dust, sand, moisture. Also, because it's a pressurized vessel, it suppresses partial discharge and also increases the level of voltage that is required for a component to break down. Hydrogen is not an oxidizing agent, another benefit. And pure hydrogen will not support combustion. This is pretty important right here, that as long as your hydrogen is pure, you have no problems as far as explosion or fire. This is a sectioned view of a hydrogen-cooled generator. I'll point out some of the important features. Why I am showing this is because we need to keep the hydrogen inside the generator. So all of the coils, all the electrical components are housed inside an iron case. Also, where you run into issues or problems is where the rotor, the rotating part of the generator, penetrates the generator, where it comes in and out of the generator. You will note on the left-hand side a hydrogen seal. And this seal is what keeps the hydrogen from escaping from the generator. This seal is on the turbine end of the generator. There is another seal on the exciter end of the generator. Also, you can note in this that there's a hydrogen fan on the left-hand side of the generator as well as on the right-hand side of the generator. Some generators have one fan, some of them have two. Another place for hydrogen to escape is any penetration in the generator, such as the bushings and lower leads, any manhole covers. Those are potential for hydrogen leak, although the biggest potential for a hydrogen leak is on the seals in the rotor. This is a sectioned view of a hydrogen seal. The way that the hydrogen seal works is that you have pressurized oil that comes in contact with the rotor. On this particular seal, the pressure is 95 psig. Because it is at a higher pressure than the hydrogen, which in this case is 90 psig, the oil will flow towards the generator or towards the hydrogen section, and it will also flow towards the air section. And this flowing hydrogen is what creates the seal and this flowing oil is what keeps the hydrogen from escaping from the generator. This is what happens if you don't keep the hydrogen inside the generator. This generator happens to be located in South Africa. What the problem here was that the seal on the exciter end, which is closest to us, escaped into the exciter cab. The exciter cab has a collector ring in there, and that collector ring, if not aligned properly, can have some arcing and sparking that takes place. In this case, the hydrogen escaped into the exciter cab. There was some arcing there that caused the explosion, which then caused the fire in the generator. You do not want to come into work to see this the next day. This is the same generator. You can see that the exciter cab, which is normally closer to the generator, has actually been blown away from the generator. Why do we want to monitor hydrogen purity? There are two reasons. Safety is one reason. Hydrogen is an explosive gas when mixed with air, and the range is from 4% to 75%, and it's most explosive at about 13%. So you want to keep the hydrogen pure. You want to keep it above that 75% range. And we also want to measure the hydrogen purity because of efficiency. The purer the hydrogen, the less windage loss that you have, so that you can generate more megawatts. You typically, on a generator that has vacuum seals, vacuum-treated seal oil seals, you would like to keep the hydrogen purity at approximately 96% or higher. We also monitor gas purity during the gassing and degassing of the generator, or purging of the generator. And we also monitor the hydrogen purity during the normal operation of the generator. This chart indicates the effect of having pure hydrogen. As you can see, the purer the hydrogen, the lower the windage loss, which equates to lower financial losses. There are two different slopes. One is for a 400 megawatt generator, less financial impact with the having higher purity versus lower purity, and then an 800 megawatt unit, which you can see it's significant that when you go from 91% to 98 or 99%, the windage losses that occur and the loss in financial dollars. This is a typical hydrogen p&id for a generator. And I'm going to point out a few components that are in here. In the lower middle of the page is the purity analyzer, and that's what we're going to be discussing. What I'd like you to know is where the sample for the purity analyzer comes from. Now, during normal operation, the sample will come from the generator fan pressure. It will go through a filter and a moisture indicator. There's a three-way valve that will direct it towards the analyzer. It goes through a flow meter, through the analyzer, another three-way valve, and then back to the generator fan suction. So this particular analyzer is connected across the generator fan. It is relying on the generator fan pressure to create a flow through the analyzer. Now, if the generator fan, if this was not connected across a generator fan and just connected to the case, the three-way valve on the outlet of the analyzer could be turned towards vent, and then the flow would exit the analyzer and go to vent versus return to the generator, and you would be using some hydrogen to measure the purity. So under normal operating conditions, you got your hydrogen coming from across the fan in the generator. Now, during the purging process, which I'm going to discuss in a little bit more detail later, the three-way valve that you see below the flow meter that is labeled Cal Purge we would put that in the CalPurge position, and then the analyzer would either be getting gas from the calibration gases, which would be the H2 calibration gas, CO2 calibration gas, or nitrogen calibration gas. By the way, we use nitrogen as a calibration gas instead of air. It's just because it's not explosive when mixed with hydrogen. Or you can see that there's another line that goes up into the vent. This is very important because this is where we will take our purge sample when we're purging the generator, and we'll discuss that later. Also on this page, you note that there's some transmitters and gauges for the hydrogen supply. There's transmitter and gauge for the CO2 supply. There's a differential pressure transmitter and gauge that's measuring the case pressure. And then there's a there's a pressure gauge and a pressure transmitter to measure case pressure. And then there's a differential pressure gauge and a differential pressure transmitter to measure the generator fan differential pressure. This is a picture of a typical generator gas analyzer panel or a hydrogen purity panel. This, you can see, has the generator fan differential pressure gauge. It has a case pressure gauge. There's in the lower left-hand corner is a moisture indicator. That's coming from a filter, and that filter is used to keep moisture and oil from getting into the analyzer. And then the long black item is a flow meter, and then to the right of that is the analyzer control panel. What goes along with this analyzer, there would be another box or enclosure that would house the electronics, and then there would be another enclosure that would house the sensor cell. All of the isolation valves on this slide or this picture are just used to control the gas that's coming in and out of the analyzer. There are different methods used to measure gas purity. When hydrogen-cooled generators first come out, they were using a manometer, and what this was is a glass U-tube that was filled with mercury, and it would monitor the differential pressure across the fan. What the manufacturer did is created a chart that would convert differential pressure to hydrogen purity. So along with the manometer, there would be a chart, and that you would have to take the reading on a manometer, go to the chart, and convert that to gas purity. You can also use gas density blowers to monitor hydrogen purity. This operates similar to manometer. It's measuring differential pressure. And then that differential pressure is taken and converted into a purity. With a gas density blower, this is done electrically. And then probably the most common type of sensor used in analyzers is thermal conductivity, which uses a thermistor. And although there are many manufacturers of analyzers that use thermistors as the sensors, the way that they convert the signal from the thermistor to a purity varies greatly, and you have to make sure that when you're investigating what type of purity analyzer to purchase, that you're getting one that's going to be stable and accurate. And a newer technology that's now being used is a vibrating element. With all of these analyzers, it's very important that they are calibrated correctly and that they stay in calibration. And one other thing to note is that all of these analyzers will be affected when oil gets into them, so it's very important that you keep oil out of the sensors of these purity analyzers. Considerations when you're buying a hydrogen purity analyzer, I would say the top two are accuracy and stability, and I would put them on equal ground. All analyzers are accurate right after you calibrate them if they're calibrated properly. Not all of them are stable. So stability in my mind is as important as accuracy. When you are speccing out an analyzer, you want to make sure that the drift, it has a very low drift factor and that the unit is stable. I would also recommend, as far as ranges, that is a triple range analyzer, and that you want it to measure hydrogen and air, you want it to measure hydrogen and CO2, and you want it to measure air and CO2, so that you can use it not only during normal operation, you can use it during the purging of the generator. Some manufacturers and some utilities like to have redundant analyzers. The sample location of where the hydrogen sample is coming from the generator is, again, very important. We discussed it a little bit when I showed you that p&id. We will discuss it again when I discuss purging the generator. You want to have filtering on it, again, to keep moisture and oil from entering the sensor. And you want to put it in a location where the flow is going to give you a representative sample of the hydrogen in the case, and that this flow is not interrupted. Another important or very important consideration is area classification. Because you're bringing hydrogen into these analyzers or into these sensors, that area becomes a hazardous location. You need to have analyzers that are rated to be installed in a hazardous location. When you are purchasing an analyzer that has the controls and electronics that got to be in a safe area, you need to make sure that the sensor cell is the only thing that's mounted in the hazardous area. As far as requirements, different countries have different requirements. In the U.S., most power plants will go by North American Electric Code for Class 1, Div 2, Group B piece of equipment. In Europe, it would have to meet an ATEX requirement. In Australia, it might be IEC-EX. So depending on the country that you're in will depend on the area classification that the piece of equipment needs to satisfy. Now I'm going to spend some time talking about purging a generator or gassing and degassing a generator. I'm doing this because there has been several incidents in the United States over the last couple of years that have resulted in loss of life, and I think this is a very important topic. The first thing, and the first two things, which are probably the most important, you need to have updated and understood standard operating procedures. You need to have a current p&id. And the reason I'm saying updated and current is because when I first got into this business, we would purge a generator every 18 months, every 24 months. The outages were more frequent. Now outages are going 5, 7, 10 years. So the person that purged that generator 10 years ago might not be with the company anymore. We are all aware that the pool of skilled labor is getting much smaller in the utility business, and we're also aware that power plants are cutting back on people. And with this, we're losing skilled people. So it's very important that you have, again, an updated and understood standard operating procedure, and that the p&id is current, that nothing has been added to the p&id, such as switches or transmitters or gauges. You need to make sure that they're on the p&id and you know where they are. Along with verifying that your p&id is current, you need to verify that all the valves are labeled properly and that these labels are noted in the standard operating procedure and in the p&id. Over years, many of these valves will lose their labels or they become unreadable, so you need to make sure that the valves are properly labeled. You need to verify that your gas analyzer is operating properly and that it's calibrated. I would recommend also that you have a portable analyzer to support what the readings are that you're getting out of your permanently installed analyzer, redundancy, if you will. I would also recommend that you have a portable hydrogen sniffer, because some of the valves that you're going to be turning during this purging process haven't been exercised for, again, 5, 7, 10 years. And the packing could have dried, but you need to make sure that the piping that you're working with, the valves that you're working with, the fittings that you're working with, that there's no hydrogen leaks, and therefore I would recommend the use of a portable hydrogen sniffer. If you cannot get a portable hydrogen sniffer, at the very least you should have a liquid leak detector to detect any potential leaks. On the bottom of this page, I got operations and I&C involvement. The reason for this is that I think it's very important that you have 2 people purge a generator. And it would be, and this is from experience, I've witnessed purging of a generator where the operations were involved and the I&C group were involved. You can have one group one person that's reading the standard operating procedure and looking at the p&id, and you can have another person that's actually exercising the valves and also reading the p&id. This is a section view of a hydrogen-cooled generator. We're going to talk right now about the hydrogen purging process. But before that, the 2 pipes exiting the generator on the lower left-hand side, this is where the analyzer gets its sample during normal operation. And those 2 lines are coming from the generator fan pressure and the generator fan suction. During the purging process, you're going to want to have the analyzer taking its sample from a different location, and I'm going to explain this in a minute. But when you come out of an outage, this generator is filled with air. And you don't want to put hydrogen in the generator when there's air in the generator, so we want to use an inert gas to remove the air. In this case, we're going to talk about using carbon dioxide as a purge gas. There are manufacturers and there are utilities that will use a different gas or different gases, but we're going to, in my explanation, we're going to use carbon dioxide. So this generator is filled with air, and I want to get that air out of there. So what I'm doing is I'm connecting my CO2 supply to my CO2 feed line, and I'm going to be pushing carbon dioxide in the bottom distribution pipe. Because carbon dioxide is heavier than air, it will create a blanket, and as I put carbon dioxide in the generator, it's going to force air out the hydrogen distribution pipe on the top. So I want my analyzer located on the hydrogen feed line that's coming from the hydrogen distribution pipe. So as I fill that generator with carbon dioxide, the air is coming out of the hydrogen distribution pipe, exiting to the vent. Now, you will note that if I was still taking my sample where I take it during my normal operation, as soon as I start to put carbon dioxide in this, because those points are at the bottom of the generator, they're going to see carbon dioxide immediately, even though the top half of this generator's got hydrogen in it, or air in it. So it's very important that where you're taking your sample from. After I have this generator filled with carbon dioxide, now I want to get rid of the carbon dioxide and put hydrogen in there. So what I'm going to do is connect my hydrogen feed to my hydrogen supply. I'm going to move my analyzer now to the CO2 feed line that's going to vent, and I'm going to start to put hydrogen in through the hydrogen distribution pipe. Because hydrogen is a lighter gas, it's going to force the CO2, which is the heavier gas, out the bottom distribution pipe. And again, my analyzer that I'm using to read the gas in the generator will not see hydrogen until hydrogen has completely forced the carbon dioxide out of the distribution pipe in the bottom of the generator. Back to the p&id that I showed you earlier, and again, under normal operating conditions when the generator is running, I'm going to be taking my sample from the generator fan pressure and the generator fan suction. During the purging process, I'm going to take the three-way valve on the bottom of the flow meter, change it so that it's taking the sample from the right-hand side, and I'm going to have the isolation valve that's in line with the purge open, and that goes to the vent from the generator as we discussed in the previous slide. So now my sample is going to come from the vent line of the generator. Up in the, just for, to note, the CO2 supply, the hydrogen supply, the air supply, they're at the top of this drawing. They go through a manifold that has valving that will put the gas in the correct pipe for you, and then you can see on the right-hand side the H2 and air supply to the generator, the CO2 to the generator, and then the vent from the generator. This is a typical hydrogen control cabinet. In the upper right-hand corner, that's the gas analyzer. Again, you have fan differential pressure gauge, case pressure gauge, a flow meter to monitor the flow into the analyzer control and display panel. Also on this, below that panel, you see the CO2 supply pressure, hydrogen supply pressure, and then to the left-hand side is the manifold that is used to put the gas in and out of the generator. One item that I would like to point out on this is that in the drawing, in the upper right-hand corner, you see what is called the hydrogen/air spool. The reason for this is that you don't want to have the ability to put air and hydrogen in a generator at the same time. So this spool is used to feed each of the gases so that it can only be in one position to either let air into the generator or put hydrogen into the generator. That piece is in the upper left-hand corner. It's a U piece of tubing. It's where the three flanges are, and you see that it can either be in one position or in the other position. One for air, one for hydrogen. This is a picture of a portable gas analyzer, which again I recommend that it be used during the purging of the generator. This is for temporary installation. It is not meant to be installed permanently. It is also meant to be used in an area that is well ventilated where you don't have a chance for hydrogen buildup. Now we're going to talk about Dewpoint. Why do we monitor Dewpoint? I personally think we monitor Dewpoint because of component and insulation failures. There is an efficiency effect as a result of Dewpoint change, but I think it's minimal in that and I'll show a chart that actually confirms that, but there are some companies, there are some utilities that feel that higher Dewpoint results in having a less efficient generator. Oh, by the way, back on this slide, this is all about risk mitigation. It really doesn't have anything to do with safety. However, if you lose a retaining ring, which we're going to discuss in a few minutes, it potentially could become a safety issue. Increased dew point can lead to insulation failure or electrical cracking in the machine. There's an excellent paper that is written by the late Don Albright, who founded Generator Tech, that discusses this in detail. And if you could either get a copy of that from Generator Tech, the company. I believe it was presented at an EPRI conference, so they may have a copy of it. If not, I have a copy of it, and you can get in touch with me, and I can give you a copy of it. So one of the reasons you want to keep your dew point low is because of insulation failure, also because of the corrosive effects that increased moisture could have, particularly on the retaining ring. The retaining rings are the most highly stressed mechanical component in the generator. So you want to make sure that they keep their integrity. Years back, the retaining rings were built with 18.5 stainless steel. 18.5 stainless steel was susceptible to moisture, causing cracks in the ring, causing it to fail. Rings nowadays are made with, I believe, 1818 stainless, and it's a far better stainless. However, you still don't want moisture in your generator, and moisture can still have an effect on 1818 rings. One other thing is, years back, again, when I got back into this business, most generators were base load units. They came up, they ran, and you didn't take them offline until your outage. Nowadays, there's a lot of cycling that's taken place with generators. There's a lot of combined cycle plants, peaking units that will operate once or twice a day, and they'll operate for a couple hours. The problem with this is that the gas in the generator is heating up and cooling down. And that heating and cooling effect can cause the moisture in the generator to condensate. So the high dew point, along with cycling of the generator, that could cause problems in the generator. This is what happens when a retaining ring lets go. This is not a pretty picture. This is what an insulation breakdown would look like in a generator. This is actually the rotor turns that are located underneath the retaining ring. Again, there's a paper that was written by Don Albright of Generator Tech that it goes into great detail on the effects of moisture on turns in the rotor. This chart indicates the effects on density that hydrogen has and what dew point has. You can see that the pink line, which is dew point, when you go from plus 50, oh, by the way, I forgot to mention that what is a good dew point? It should be a negative number, negative degree C. Most manufacturers will use 0 as an alarm point. So here you see that when it goes from plus 15 degrees to minus 5, there is a change, but it's minimal. It's not much of a change. And when you're down below, down in the area of negative 5, and you go to negative 35, there's hardly no change, or virtually no change at all, in the effect on density that the moisture has. However, you can see that the purity, which is the blue line, has a major effect. So when you go from 95 to 99 or 100%, the density changes considerably. Where does moisture come from? The primary source is the seal oil. In many large power plants where you have steam turbines, in some cases they share the oil source. So the steam seal or bearing on a steam turbine will absorb moisture from the steam and then be carried over to the generator where it goes into the generator. As long as your seal oil treatment equipment is working properly, there's no issue. But if that breaks down, you can get moisture in your seal oil, which will result in moisture in your generator. You can get moisture from your hydrogen coolers. You can get moisture, if it's a stator-cooled winding, you can get water from the stator cooling water. And again, you don't get moisture from thermal cycling, but the thermal cycling will cause condensation if there is moisture in the generator does have a high dew point. Methods of monitoring dew point, there's several methods. You can use a ceramic sensor, a silicon-based sensor, aluminum oxide sensor. Chilled mirrors, I'm not aware of chilled mirrors ever being used in a generator, although chilled mirrors are the standard outside of a generator. All of the top 4 sensors, the ceramic, silicon, aluminum, the top 3, they're measuring a change in the electrical properties, whether it be capacitance, resistance, or impedance, and that's how they're determining the dew point. You can see the considerations are similar to that of the hydrogen purity. You want it to be accurate and stable. One additional thing with dew point is you've got to make sure that the sensor that you're using has pressure compensation. If the sensor is calibrated at atmosphere, when you put it in the generator, which is under pressure, you may have to compensate for that. You need to know what the effects of temperature changes are. If you have major changes in your hydrogen temperature, you want a constant pressure. The sampling location, not as critical as a hydrogen purity analyzer. However, you don't want it downstream of filters. You don't want it downstream of a hydrogen dryer if you have a hydrogen dryer. You want the sample to be representative of what the hydrogen is in the generator. Again, area classification, you're bringing hydrogen into this sensor. When you bring hydrogen to this sensor, the area becomes a hazardous area. Again, different countries have different requirements. In the United States, the North American Electric Code, for Class 1, Div 2, Group B requirements. In closing, by using hydrogen as a cooling medium, you can get more megawatts without increasing the size of the generator. More megawatts means larger generator, bigger generator, more iron, more heat. For reasons concerning safety, efficiency, and risk mitigation, it's very important that we know what the purity of the hydrogen is. Before purging, we need to make sure that our standard operating procedures are up to date. Our p&id is correct. Our valves are labeled correctly. When we are measuring dew point, we're mitigating risk. High dew point in generators can lead to component failures. All of this is about safety, increased efficiency, and risk mitigation. Thank you.
Well, thanks so much for your presentation, Steve. We've actually had a ton of great questions come in from the audience during the course of the program. So we will try to consolidate similar questions and answer as many as possible with our time remaining, which we're trying to stick to a 60-minute time slot. So for those questions we are not able to answer due to time constraints, we will definitely try to answer individually by email following the program. You can also access E1's website anytime at www.e1.com/solutions, which you can see on the last slide right now. So Steve, the first question for you to answer, as there are many, what if I don't have an SOP, standard operating procedure, for purging the generator?
As I mentioned in my presentation, this is critical, and if you do not have one, you need to create one. And in most cases, I know with, for instance, a General Electric generator, they have what's called GEKs. And in the GEK, they have the purging process. So If a power plant has lost it or they do not have it, I would first start by going to the OEM and see if they have a copy of the original, in General Electric case, original GEK that was supplied with the generator. If you do not, you should create an SOP and have someone that is familiar with purging a generator involved in creating your own.
Okay, great. Next question, how can I be sure that my p&id piping and instrumentation drawing is correct?
By brute force. You need to walk down the generator. You actually need to trace the piping from the generator into the hydrogen control cabinet, identify all the components that are inside the hydrogen control cabinet. It's done manually, and if the p&id is old, I recommend that either you can contract the work out or have someone in the power plant walk through the p&id and verify that that p&id is correct.
Okay. Next question for you, what is the difference between hydrogen and nitrogen as a coolant?
Pretty much the same as air, hydrogen and nitrogen and hydrogen and air. Hydrogen being, again, far lighter, far less dense, has better heat removal characteristics. Nitrogen, although it might be a little bit better than air, it's still a heavier gas similar to air, and I'm not certain about its heat removable characteristics, but I would suspect that it's similar to air.
Okay, great. The next question for you is, I intend to manufacture hydrogen and I need help. Whom should I talk to?
Proton Energy. They make hydrogen generators, and there's actually a few companies out there that make hydrogen generators. Proton Energy is one of them. Actually, we have an engineer that works in our group that used to work on making hydrogen also, so you could contact Environment One. Our director of engineering name is Gus Graham, and he's very familiar with the manufacturing of hydrogen.
Okay, great. Now, there's a question about a newer plant that was built in a particular user's area. They're using gas turbines without hydrogen-cooled generators, but air-cooled. You understand the output of this generator, 232 megawatts. They've had 2 of the 3 units down for generator rewind. The question they have is, why would the manufacturer of this type of generator not use hydrogen cooling?
Different manufacturers use different cooling techniques depending on the size of the generator. And I'll give you an example. Siemens and Alstom will make some very large air-cooled generators in the neighborhood of 250, 300 megawatts. General Electric chooses to cool generators in the neighborhood of 100, 125, 150 megawatts with hydrogen. So it depends on the philosophy of the OEM as to when they will begin to use hydrogen as a cooling medium. Again, Alstom and Siemens will cool some very large generators with air, whereas General Electric chooses to use hydrogen on very small generators.
Okay. Next question, as we continue to roll on, our generators are furnished with GCMX monitors. For a few days after the unit is at full power, ops has to constantly adjust H2 flow to clear the local alarm. H2 press and temperatures remain relatively constant after the unit achieves full power. What can cause a gas flow to deviate from the preset flow rate?
I'm not sure if it's a gas flow issue. I'm very familiar with this piece of equipment, and typically after an outage, depending on how long the outage is and depending on the condition of, was CO2 put in the generator and the GCMX isolated. But normally what we see is when you come out of an outage, moisture can form in the ion chamber, and it takes several hours to several days for this moisture to be removed from the ion chamber so that the output stabilizes. So I would certainly like to talk to whoever sent in this question, and we'll address his concern further. But I suspect that it's more that he's coming out of an outage and it's taken time for the unit to stabilize, meaning the output of the ion chamber.
Okay, great. So even if your system is well maintained and sealed, does the hydrogen break down after a while? Do the actual atoms start to break down or form H2 or H3, etc.?
No. If your hydrogen is, if you have a well-sealed generator, now all generators leak, and the leakage rate, it could vary from 300 standard cubic feet per day to, I've seen them as high as 1,500. But if you've got a generator that is tight and you've got well-operated seals, you're going to have to keep replenishing the hydrogen, but I'm not aware of hydrogen ever breaking down.
Okay, next question for you. How much do you think moisture affects the purity?
I think it affects it very little. And the problem with me saying that is that it seems like it's common sense that if I got higher moisture in my purity is going to be lower. But when you, as I indicated in my one chart, when you go from plus 15 to negative 15 in Dewpoint inside of a generator, there's minimal change in the density, and in that case you would see virtually no change in the hydrogen purity.
Okay, Steve, another one for you as the questions continue to flood in. Would there be a significant amount of moisture if cycling from 650 megawatts to 300 megawatts and back to 650 on a daily basis?
I don't suspect so. What they could look at is what their cold gas temperature is staying at and what their warm gas temperature is staying at. But I don't suspect if you're going to go from 300 to 600 megawatts throughout the day that you're going to notice a big temperature swing in the hydrogen gas of the generator.
Okay. What is more accurate, thermal conductivity or vibrating element density meters? That's
a very good question. It depends on the thermal conductivity analyzer that you're using. I'm speaking now as a salesman. The Environment 1 analyzer, as far as thermal conductivity, is one of the better ones on the market. It's very stable and very accurate. That being said, Yokogawa's vibrating element analyzer is also very accurate and very stable. I would actually put our analyzer and the Yokogawa analyzer in the same classes, that they're of equal accuracy and equal stability.
Okay, great. Now, are modern generator hydrogen systems equipped with automatic valves for purging?
I'm aware of one manufacturer that did have, and I believe they still do have, solenoid valves that they can do an auto. When I say automatic purging, this is automatic emergency purging. They want to degas the generator quickly. It's not used for purging during an outage when you're going to do some routine work on the generator. But some manufacturers do have solenoid valves. We've actually manufactured manifolds for OEMs that do have solenoid valves on them, or actuated valves, so that they can do an automatic emergency purge.
All right, next question for you. Can the dew point be too low?
Another good question. I have been told that if the hydrogen dew point gets too low, it can actually act as a sponge and remove moisture, pull moisture from the oil into the hydrogen. A good dryer, hydrogen dryer, will bring the dew point down into the negative 60 range, which I believe is as good as you need. I wouldn't want to go any colder than that. I honestly can't answer that question. I'm not certain if you can have too dry of hydrogen. I'm not absolutely certain.
Now, is it best to purge on turning gear or not on turning gear?
The benefits of doing it while you're on turning gear is that it may eliminate some pockets of gas that may form in the generator. But there may be a small benefit of purging while you're on turning gear. However, I don't think it's that important, whether you're at standstill or if you're turning the rotor. The rotor is turning at a very slow RPM and would just get rid of pockets of hydrogen that, if it's a hydrogen-cooled rotor, if it has passages in the rotor, may be trapped in the rotor, and that hydrogen would flow out of the rotor as you're turning it. But if it's I don't think it would have any effects on the stator winding as far as purging.
Anytime you mention a fan in this presentation, you're referring to the rotor-mounted fans inside the generator case?
That is correct, yes. In some manufacturers, some OEMs will use fans. Some will use only one fan on the rotor. Some will use two fans. And some use a device that's called a blower and not a fan. So, yes, I am referring to the fan or blower that is located inside the generator case.
Okay, and what frequency do you recommend for calibrating a thermal conductivity meter, a gas density meter as well?
I can only answer for my piece of equipment, and we recommend every 6 months. I'm aware of analyzers that remained in calibration past a year, but our recommendation is still that the unit be calibrated every 6 months.
Okay. A couple more questions here as we begin to get close to our hour mark. What is the acceptable makeup rate of hydrogen in 600 megawatt generator when even minor leakages are there?
As I mentioned earlier, I'm aware of generators that are pretty tight that would use maybe 300 to 500 of cubic feet per day. I'm aware of generators that are very, I'll say, not tight, that leak, that are in the neighborhood of 1,500 cubic feet per day. I would say in the neighborhood of 700 to 800 cubic feet per day. However, I would refer to my OEM's recommendation, or what the OEM says is the acceptable leakage rate for their particular style generator.
All right, last question for you as we wind down. Does presence of foam and seal oil imply the presence of moisture in a generator?
Not necessarily. Although you don't want oil in a generator, in most cases oil is in there. I'm aware of generators that have been taken apart that has standing oil in the belly of the generator, and the particular generators did not have a dew point issue. So no, oil is not an indication of high dew point.
All right, great. Well, there's still a ton of other questions, but we're going to have to get to those, as I mentioned before, after the program, as many as we can individually by email. So as mentioned, we will address those questions by email, and if you'd like to view the program again, It will be archived at www.powermag.com/turbowebinar, the same link that you viewed this presentation in. I know we had a number of questions come in asking where they could see the archive, and that's exactly where it is, powermag.com/turbowebinar. So thank you so much once again to E1 for underwriting today's event. Thank you for attending. We hope you all benefit from today's presentation. Thanks so much, Steve. Everyone have a wonderful day.
Thank you.